In this video, we're going to look at magnetism for GCSE science. So the most basic thing that students need to be able to do is, of course, draw the magnetic field around a bar magnet. So this is a skill they should have from Key Stage 3, but you can never be too careful. So let's draw the field. So we need to draw some field lines that go out one end and come back the other end. And then we need to draw some field lines that don't join up, and these represent the ones that actually go really, really far into space. And then we need to draw the arrows from north to south, which is the convention. So this is an acceptable drawing. We don't have to draw too many lines. This is enough. You could draw a smaller one here as well. There'd be nothing wrong with this at all, but we've probably drawn enough. Now, bad drawings would be things that include some of the following mistakes. And weirdly, you often see these bad drawings on the internet or in textbooks as well. So any bad drawings, if we have field lines coming out from the same place, that's bad, right? Because if they go into the same place, how can they go in different directions? That doesn't make any sense. If we have field lines that have gaps, all right, again, that's bad because the field lines are continuous. And obviously, if the arrows go the wrong way, that is bad as well. These are the most common mistakes, right? This mistake here is made very common. It's very common by students because they just try to put far too many lines into a drawing like this. You need to encourage them to do only a few lines. So when we talk about fields, right, we could be talking about magnetic fields, and often we use B fields, or A level we probably wouldn't use as a GCSE. We could be talking about electric fields. We could be talking about gravitational fields, or we could, there's other types of fields. There's the Higgs field, if you want to go into particle physics. But these are the ones that students come across at GCSE. What do we really mean by a field? We just mean something that is defined at all points in space, which doesn't necessarily mean a lot at GCSE, and it's not really even a definition you need to know. But what this basically just means is it means the magnetic field or magnetism is infinite in range. All right, and there's no gaps in the lines. That's what we really mean by this. So if I have a bar magnet here, and I go to the moon, right, that field still extends to the moon, extends past the moon, right? It's obviously going to be far too weak to be noticeable, but mathematically it is there. Other really basic things, of course, that students should know. They should, of course, know that north and a north pole repel each other. They should know that a north and a south pole attract each other, and then the south and a south pole repel each other. Students should also know that there's no such thing as a monopole. Okay, having a north pole on its own or a south pole on its own doesn't make any sense in magnetism, right? And as far as we know, this is completely true in physics, right? You can't have this, right? We always have a north and a south pole, and if you chop a magnet in half, you end up with a smaller north and south pole. You chop that in half again, you end up with a smaller and smaller and smaller north and south pole. One other thing to do with fields as well, because they have arrows on them, what does this immediately suggest about magnetic fields, or equally electric or gravitational fields? It suggests they are vector fields, right? Or that what we're dealing with is vectors because they have a size plus a direction. And it's always worth making these links between what students have studied in other topics and what they're coming across in new topics. Right, the arrows are really important because they show us the direction of the field. So that becomes important because if we're dealing with, for example, a south pole and a south pole from two separate magnets, okay, obviously these would be north poles at the other end. What does this field look like? Well, these are going to repel each other, so the field is going to do something that looks like this. Probably worth drawing a couple of lines from each one. All right, so the arrows need to go from north to south, so they'll be going in. Okay, so at this point here, all right, there is zero field. Okay, an object placed here would not experience any force whatsoever. This would look exactly the same if it was a north pole and a north pole, but the arrows would just be reversed. Students should be able to draw and recognize these. If you want to challenge them, you could do some kind of complicated arrangement where you have north, south, south, or you could do, 8 or something. And these have uses in particle physics because you can make these quite complicated fields where there is basically no force in the middle, and any particle in it will be repelled from the field and made to stay in the middle. So if you're trying to trap particles, magnetic fields are really, really useful to do this. They probably use electric fields as well and have a combination of them for various reasons, but for a very simple level, we can just explain that these can be used to trap particles, or more specifically charged particles. All right, I won't talk about it in this video in any more detail than this, but it becomes more important when we're looking at electromagnetic induction. Charged particles moving in a magnetic field feel a force. Right, and this is really, really fundamental to physics. This explains how we can generate electricity, and it explains, so many other different things as well. So it's always worth, highlighting this. So the type of magnetism we're looking at here is called ferromagnetism, and this is basically permanent magnets. So these are the magnets you have in your fridge, the magnets we're used to. So we should know that iron, nickel, and cobalt are all ferromagnets or ferromagnetic. They are permanent magnets. Sometimes as well, gadolinium is also mentioned, but AQA really only requires these three. And then recently, and when I say recently, I think this was about between 20 and 30 years ago, they discovered neodymium magnets as well. Which are a combination of neodymium, iron, and boron, and these make super strong magnets. Now, students don't need to know this, but they will of course know about neodymium magnets because they're everywhere now, and a lot of them will have them and play with them, and they are really useful magnets to have because they are so much stronger than regular magnets. You can show some really interesting effects. One thing that you can demonstrate with these, and I'd highly recommend showing this because it's really interesting, you can demonstrate the phenomenon of paramagnetism and diamagnetism. Now, these are definitely not on the GCSE syllabus, but they're really interesting. So paramagnetism is a type of magnetism that is always attractive, and diamagnetism is always repulsive. Okay, there's no attraction and repulsion. It's always one or the other. So an example of something that is paramagnetic is water. So you can look up the levitating frog video. That's really interesting. Or you can do a really nice demonstration with grapes. Right, if you get some water and you float a grape on it, and then you get a really strong neodymium magnet on a stick. So we have these in the prep room. The grape will be attracted to the magnet, right? And then you can talk about how strong these magnets are compared to regular magnets, and you can kind of stretch students with these really interesting phenomena. Although in truth, this is not something you even do at A level. This is something that you probably learn about on a physics degree. A similar variation of this, if you just get a piece of cotton and then you get a stick, and on the stick you just suspend 2 grapes, then you can get the really strong magnets again, and they will rotate towards it. Diamagnetism, an example, is aluminium. So again, you can either float some aluminium on water, or you can stick 2 screwed up balls of aluminium on a stick attached to a cotton thread, and you'll be able to repel the aluminium with the super strong neodymium magnets that we've got. Back to what we actually need to know for the GCSE syllabus, we need to have a little bit of understanding about what actually causes magnetism. So if we have some lump of ferromagnetic material, for example, a lump of iron, then why are things magnetic? Well, if you look at the iron, in detail under a microscope, you basically see that there's these domains, and in these domains, there are mini magnets that are pointing in random directions. Now, because in the average lump of iron, these arrows are pointing in every single direction, overall they cancel out and there is no magnetic field. But if you can get all of these magnetic domains and you can line them all up and point them all in one direction, then all of these mini magnets line up. And what have you created? You've created a noticeable magnetic field. So how do you get from here to here? All right, how do you make a magnet? Well, there's a couple of ways you can do it. All right, you can put it in a very strong magnetic field. Right, if you put it in a strong magnetic field, all of these individual domains will all point in the same direction because they're being forced to by this very strong magnetic field. Or what you can do is you can get a regular bar magnet, again fairly strong, and you can basically just kind of stroke it on the magnet, and every time you stroke it, you're basically doing exactly the same here. You're just encouraging them to flip and point in the same direction. So that's how we create a magnetic field. How can we destroy a magnet, or how can we break a magnet? Well, we obviously need to undo this. We need to make all the domains point in different directions. So there's a couple of ways we can do this. If we hit it really hard with a hammer, for example, we can provide enough energy to these domains to jumble them all up again, and we can destroy our magnets. So if you shouldn't drop magnets. If you leave them in a strong magnetic field that is not necessarily aligned with it, like if you put them just a load of magnets in a box together, again, all the little magnetic fields will mess with these, and over time will weaken the magnet. And then finally, heating the magnet as well will cause all these domains to jumble up again, because you're providing them with energy to go against this direction. So the point at which a magnet loses its magnetism, if you put it in, if you heat it up, is known as its Curie temperature. And this is not something that you need to know for GCSE, but if you ever see this word Curie temperature, that's what it means. There's a really good website, table.minutephysics.com. This is an interactive periodic table where there's a temperature scale, and you can slide the temperature along, and it will tell you at what temperature every single element changes its magnetism when it becomes ferromagnetic, or if it becomes paramagnetic or diamagnetic. And what's quite surprising is if you decrease the temperature, a lot more elements than you might expect actually become ferromagnetic. But at room temperature, these are the ones that we care about. Minute physics in general is really good. There are some really good videos on magnetism, along with veritasium as well. And they explain this idea in a lot more detail than I do. And then they link it to electromagnetism and induced magnets as well. So highly recommend checking out Minute Physics' channel on YouTube and Veritasium's channel on YouTube.